All right, welcome everyone. This is our first members colloquium for the year. So the members colloquium is a general lecture series for across all mathematical fields. And let me just take the opportunity, if you're a postdoc here, to really try to come to this even when it's not in your field. Okay, you will learn something useful, and you'll all be in a position where you have to give a broad talk, and the only way you can learn to do that is by watching other people do it. Okay, and I'm very pleased that our first talk will be by Jacob Lurie, who will tell us a little bit about the special year and rigid analytic geometry.
All right, thank you. So as you might know, every year is a special year in the School of Mathematics. This year is special because we have a lot of experts in P-adic geometry around. And so I see a lot of those experts are here in the audience. They made a mistake. This talk is not for you. I apologize. What I want to do is communicate to the rest of you something of what this subject is about. So roughly speaking, P-adic geometry or rigid analytic geometry, it's a version of the theory of complex manifolds, where instead of using complex numbers, you use something like P-adic numbers. So in this talk, I'd like to say a little bit about all of the following questions that you might ask. First, what do you mean by that? Second, how similar is it to ordinary complex analysis? How is it different? Why did we think this was a good time to have a special year on this topic? What's new in the subject? And maybe most importantly, what could P-adic geometry do for you? Why? What sort of questions does it let you tackle? And let me start with this last question, right? Just giving an example of first what ordinary complex geometry might do for you if you were a number theorist. So let's start with the following question. What can you say about the set of rational solutions to this polynomial equation right here? And there's no significance to the coefficients that I chose in this polynomial. I just chose those numbers at random, but I didn't choose the degree at random. I want a degree 3 equation here. In that case, this question has a lot of structure. It's the defining equation of an elliptic curve. And if you know 5 things about algebraic geometry, probably one of those 5 things should be that if you look at the points on an elliptic curve, they form an abelian group. And here, by points, I mean, well, first, the set of solutions to this equation, where x and y are rational numbers that lie in the usual plane, but I also want to include solutions that lie in the projective plane, which means there's one extra solution that lies on the line at infinity that I'll just call infinity. And this solution set has the structure of an abelian group. And what can we say about this group? This is a very old question. So a theorem now more than a century old by Mordell is that if you look at rational solutions, that's always a finitely generated abelian group. So it always looks like a lattice of some rank plus the torsion subgroup, which is a finite abelian group. And let's ask a more specific question. What can we say about this finite group? So if you want to get information about a question like this, it can be very useful to think about solutions not just over the rational numbers, but say over the complex numbers. So let's think instead about the collection of complex solutions to this equation, again, including this point at infinity. And now there's more structure to this. This is actually has the structure of a Riemann surface, a one-dimensional complex manifold. And because this was a degree 3 equation, it's a Riemann surface of genus 1. It looks like a torus. And again, there's a group structure here. And as a group, it looks like you took the complex numbers modulo some lattice lambda. And if you don't care about the complex structure on that, just as a Lie group, it looks like, well, a usual torus, R mod z squared. And from this, you can immediately say exactly what the torsion subgroup looks like. If you're interested in the torsion points, well, that's just a copy of Q mod Z squared. Of course, this is a different question now. I'm asking about torsion points solutions that are defined over the complex numbers rather than the rational numbers. But this immediately gives you some information about the set of rational solutions, which maybe wasn't so obvious a priori. So this set of torsion points over the rational numbers, I said it was a finite abelian group, but it has to embed in Q mod Z squared. So for example, we learn from this that it can be generated by two elements. Of course, you can say much more about this question, and the question of what it can look like for a general elliptic curve was completely answered by Barry Mazur in the 70s. There's a short list of finite groups that can appear here. I don't know which one appears in this example because I chose it at random. Let's say we want to understand that. So we understand the complex solutions and we want to get back to the rational solutions. So first, we're interested in torsion points on an elliptic curve, and the collection of points that are n torsion for some integer n are defined by, first of all, there's n squared of them, right, what I said earlier, and they're described by polynomial equations. And a consequence of that is that the coordinates of torsion points are always algebraic numbers. They're not arbitrary complex numbers. They live in the subfield of algebraic numbers. So if you're interested in the torsion points over the complex numbers, that's the same as the torsion points over the algebraic closure of Q, and that looks like this group Q mod Z. But now, maybe what you're really interested in is the points that are defined over Q, but this description tells you that this Q mod Z has some structure. It naturally has an action of the group of automorphisms of Q bar over Q, this Galois group. And well, if you want to know this group of torsion points over Q, what you want to understand is just the collection of fixed elements of this Q mod Z squared that are invariant under the action of that Galois group. And so we know what this looks like. All we have to do is write down how the Galois group is acting, and then we'll understand the answer to our original question. But from the point of view that I've been explaining, that's maybe not so easy to do, because to understand that this group is Q mod Z squared, we went to the complex numbers. That is, we embedded Q into this bigger field C, and then we used a feature of the complex numbers, which is that it has a topology, and therefore the set of solutions has the structure of a manifold. And that's not very Galois group friendly. That is, this group of algebraic numbers, Q bar, it has a very complicated automorphism group, this group G, but very few of those automorphisms extend continuously to the complex numbers. The continuous automorphisms of the complex numbers, there are just two of them, the identity map and complex conjugation. And so if you were to try to exploit this analysis by thinking about the topology of the solution space, it's not going to tell you very much about this Galois action. You're going to need more information, a new idea, in order to get further on this problem. And so one idea is, well, let's not look just at the embedding of Q into the complex numbers, but other things that are like it. So let me remind you how the complex numbers can be defined. So the real numbers can be described as the completion of Q with respect to the standard metric, where the distance from X to Y is the absolute value of X minus Y. And you can work instead with what's called the P-adic absolute value. So now and for the rest of this talk, P is going to be a prime number. And if you have a rational number, then its P-adic absolute value is, well, you ask how many times P divides this rational number, and then you take, let's say that number is n, and you take P to the minus n. So This is a definition. And the point of this definition is that this shares a lot of features with the usual absolute value on the rational numbers. There's an axiomatization of what it means to be an absolute value on a field. And there's a theorem, again, more than 100 years old, that any absolute value on the field Q is more or less either the usual absolute value or it's this P-adic absolute value for some prime number P. And now you can play the same game that you do to define the real numbers here. Once you've defined the P-adic absolute value, you make the rational numbers into a metric space by declaring that the distance from x to y, it's the absolute value of x minus y, but now not in the usual sense, in this P-adic sense. So x is close to y if x minus y can be divided by many powers of p. And Q is not complete for that metric, and its completion is called the field of P-adic rational numbers, QP. Okay, what about complex numbers? So let me remind you first how the usual story works. So Q sits inside the real numbers as its completion for the usual absolute value. And the real numbers is not algebraically closed, so you can take its algebraic closure, and that's the field of complex numbers. And well, that's acted on by some Galois group, which in this case is very simple. Complex, the automorphisms of C, fixing R, there's just two of them. There's the identity and complex conjugation. So now fix a prime number P, you can try to say some of the same words. So Q sits inside this completion QP. That's not an algebraically closed field, so you can take its algebraic closure. And now a warning that this is a much more dramatic thing to do in the P-adic case than it was in the usual Archimedean case. So in the Archimedean case, you have the fundamental theorem of algebra, which tells you that the real numbers are almost algebraically closed already. Over the real numbers, there's essentially just one equation you can't solve, which is x squared equals -1. And if you throw in a solution to that equation, then you get an algebraically closed field. In the P-adic case, that is not at all true. There's tons of equations over QP that you can't solve. So this is a much bigger extension that you have to take. And as a result of that, well, this extension inherits a metric, but because it was a really big extension, that metric is no longer complete. So you can take a further completion and you get this field that's usually denoted by CP. And again, this is acted on by a Galois group of the field QP. And now just a warning, because you had to take a really big extension, that's a really big group. This is a very complicated non-abelian group. And there's a lot to say about this group and its representations. And that's one of the themes that's part of the special year, understanding this group, understanding representations of this group, particularly representations that come from algebraic geometry. Things like looking at how the Galois group acts on the torsion points of an elliptic curve. But the fact that this is a big group, it's a feature rather than a bug, at least from the point of view I was describing earlier. I said that, if you wanted to analyze an elliptic curve over Q by thinking about it over the complex numbers, well, you were not going to get too much information because you were only going to see how a very small Galois group acts. But in the P-adic case, well, this group is a much better approximation to the Galois group of Q. Well, just terminology, this field CP that you get at the end of this process is sometimes called the field of P-adic complex numbers. And the rest of this talk is going to be about to what extent does it deserve that name? To what extent can you really do things with it that you ordinarily do with the complex numbers? Like, is there some version of complex analysis, but for this field instead? So let me start by saying a few words about classical complex analysis. So let's say you have a a region in the complex plane U. So complex analysis is concerned with holomorphic functions. So a function f is holomorphic if it satisfies the Cauchy-Riemann equation. And this has many different formulations, and maybe one of the first important theorem about holomorphic functions is that they're the same as analytic functions. They're the same as functions that in a neighborhood of every point are given by a convergent power series expansion. And another important fact about holomorphic functions is that they satisfy the principle of analytic continuation. If you have a function which is defined on a large region, but a connected region, then it's determined by what it looks like on any smaller open subset. It's determined by its behavior near any point that you happen to be interested in. Okay, so that's the classical complex analysis. And now let's ask what happens over the field of P-adic complex numbers. So if you try to make definitions naively here, you're immediately going to run into trouble, and that's because we're doing non-Archimedean geometry now. This P-adic absolute value, it satisfies a very strong version of the usual triangle inequality. The absolute value of x plus y, it's not just bounded above by absolute value of x plus absolute value of y, it's bounded above by the maximum of the two. And this gives the topology that it defines a very different flavor. So what it means in particular is that this CP as a metric space, it's very far from being connected. There's tons of open sets that are also closed. And here's an example. You can look at the closed unit ball. That is the collection of P-adic complex numbers that have absolute value less than or equal to 1. And as you would expect, that's a closed set. But because of this ultrametric property, it's also an open set. So that's kind of strange. And as a result of having a strange set like that, you could define a strange function. That is, take the characteristic function of that ball, the function that takes the value 1 if the absolute value is less than or equal to 1 and the value 0 otherwise. And now this function, if you thought maybe you should demand some sort of holomorphicity condition by writing a differential equation or by demanding that it has power series expansions locally, it's going to pass all of those tests. It's locally constant. But you really don't want to allow a function like this if you want to have anything like the classical theory of complex analysis. So first, this would violate the principle of analytic continuation. Like, this function is certainly not determined by its local behavior. If you just look near 0, you would think this is the constant function with the value 1. It doesn't satisfy a maximum principle. That is, if you take a ball of large radius, it's big in the middle of the ball and it's small on the boundary. It's a function which locally has a power series expansion because it's locally constant, but even though it's everywhere defined, it doesn't have its Taylor series expanded around 0, for example, doesn't converge everywhere, or doesn't converge to the value of the function everywhere. So all three of these things are saying, this is forbidden behavior that would be forbidden in classical complex analysis. And so if we want a good theory of P-adic complex analysis, we have to disallow this function somehow. Okay, so I said it's a bad function, but really it's a bad open set, right? This function is a characteristic function, and it comes about because CP can be decomposed into these two disjoint open sets, a ball of closed disk of radius 1 and its complement. And so if you want to rule out that function, you have to say there's something bad about this decomposition. And so it was Tate in the 60s who really figured out what to say here. So Tate's idea was, well, maybe contrary to your expectation, the bad open set is this one, the one that's defined by a strict inequality, and the good open set is the one that's defined by is the closed ball of radius 1. That is, let's really embrace the non-Archimedean features of CP and embrace the fact that sets like this are open. So this open set on the left is an example of a special kind of open set that he called an affinoid domain. So I'm not going to give a definition of that, but roughly speaking, being an affinoid domain means something like it's an open set which, if you tried to describe it by inequalities, you would use the less than or equal to sign and not the less than sign. So this set appearing on the left is an affinoid domain, and this set appearing on the right is not. And Tate proved that if you restrict your attention to these affinoid domains, then in some sense, the pathologies will go away. So here's an example of something that he proved. So let's say you have an affinoid domain U and you have a function on it. And suppose that you can cover U by finitely many affinoid subdomains such that on each of those pieces, it has a convergent power series expansion. And that's also true for the original function f globally on U. So you should think of this as analogous to a theorem of complex analysis, that if you have a function which is defined everywhere on an open disk, then if you take its Taylor series expansion around the center of the disk, that will converge on the entire disk. That is, maybe a priori you thought you only had a Taylor series only converged in small neighborhoods of every point, but actually they have to converge everywhere. So Tate proved in P-adic geometry, once you get your head on straight, exactly the same thing happens. And this was the beginning of the subject of rigid analytic geometry. So the basic objects are these things called rigid analytic varieties. I'm not going to give a definition, but they're obtained by gluing together these things I mentioned on the previous slide called affinoid domains. And maybe more importantly, the functions that you study in rigid analytic geometry. Rigid analytic functions are functions which on any affinoid domain can be described by a convergent power series. And because of Tate's theorem for the previous slide, this is all a sensible thing to do. So I haven't given a definition, but you should think this is the P-adic counterpart of the notion of a complex manifold. These rigid analytic varieties, or more precisely, the smooth rigid analytic varieties, are like manifolds over the field of P-adic complex numbers. And well, with this definition, a lot of the basic principles of complex analysis carry over. Like you have notion of analytic continuation and a maximum principle and things like this. Okay, so where do you get examples of these rigid analytic varieties? You can get tons of examples from algebraic geometry. So first let's talk about the complex numbers. If you have a smooth algebraic variety over the complex numbers, something that's described by polynomials with complex coefficients, then the solution set has the structure of a complex manifold. And if you restrict your attention to projective varieties, then passing from the algebraic variety to that complex manifold doesn't actually lose any information. This is a theorem of Chow from around 1950, that if you have two smooth projective varieties, or more generally, if just x is projective, then any holomorphic function from x to y is automatically algebraic. It's something that can locally be described by polynomials. And in P-adic geometry, something similar happens. So if you have an algebraic variety, now instead of over the complex numbers, over this field of P-adic complex numbers, it has an underlying rigid analytic variety, which I'm going to denote by x with a superscript an for analytic. And passing from x to its rigid analytic variety, again, it doesn't lose any information as long as you restrict your attention to projective algebraic varieties. Any rigid analytic function between them automatically comes from polynomials. It's already something that you can see in algebraic geometry. So that makes this theory of rigid analytic varieties potentially a useful tool for studying questions of algebraic geometry. You can think of algebraic geometry as sitting inside this rigid analytic geometry in a nice way. But there's also lots of examples of things that don't come from algebraic geometry. And again, let's start by thinking about the usual complex case. Most complex manifolds are not underlying manifold of an algebraic variety. Maybe the easiest example is to take the open disk in the complex plane. Doesn't come from an algebraic curve. It's not, doesn't have a compactification by a Riemann surface with only finitely many missing points. So this open disk, it doesn't live in the world of algebraic geometry itself, but nonetheless, it could be very useful for studying things that do live in algebraic geometry. So let's say you were ultimately really interested in algebraic curves. You were interested in things like compact Riemann surfaces. Well, the unit disk is not compact, but any point in a Riemann surface has an open neighborhood which looks like this open unit disk. And that could be a very useful thing to know because this unit disk, it's something that we understand completely, at least for certain kinds of questions you might ask about. It's some very explicit, simple thing. So another way of saying this is, you could study more complicated objects like compact Riemann surfaces by probing them with things like this open unit disk, considering maps from an open disk in where, well, the domain is something very simple. So I'd like to consider a variant of this idea, which is, again, in complex geometry. If you have a complex manifold X, you can take its universal cover. I'll call that X tilde. And this is something that will definitely leave the world of algebraic geometry if you started there. So if X comes from an algebraic variety, typically X tilde will not. So passing to this world of complex manifolds gives you a maneuver, passing to the universal cover that you might exploit to try to understand the objects that you're trying to understand. And this is a really powerful maneuver in complex dimension 1 because of the Riemann uniformization theorem. So this is maybe one of the crown jewels of complex analysis. What it says is that if you have any Riemann surface at all, no matter how complicated, its universal cover is one of 3 possibilities. It's either the Riemann sphere, the complex plane, or the complex upper half plane. And so now I want to ask the question, what happens in the world of P-adic geometry? And maybe a disclaimer, I think the answer to this question is nothing like this. I've never heard of anything analogous to this theorem in the world of P-adic geometry. I don't think it's very plausible to have anything like a statement this nice, but I want to sort of meditate on approximations or to what extent this maybe fails in the world of P-adic geometry, and we'll learn something interesting. So let's start by thinking about Riemann surfaces of genus 0. Well, there's just one of those, right? First, let me note that in the world of algebraic geometry, you can study the projective line over any field K, and over the complex numbers, you can think of that as a Riemann surface of genus 0. It's the Riemann sphere, C union infinity. And as the terminology suggests, that's a sphere as a topological space. In particular, it's simply connected. And maybe something surprising is that in the world of P-adic geometry, that is not true. That is, you can look at the projective line now over the field of P-adic complex numbers. So that is something that has an underlying rigid analytic variety as a set, it's CP union infinity. And now that doesn't have any finite covers. Finite covers of this would have to live in algebraic geometry where we can rule them out. But it has lots of interesting infinite covers. So one was discovered in the 90s by Dick Gross and Mike Hopkins. In rigid analytic geometry, there's actually a non-trivial covering map from the open unit disk to the projective line. And so I don't want to say how they found this, but let me just emphasize, this is not a pathology. It's not like they were looking for a weird counterexample to something. It was actually, they were trying to understand a very complicated nonlinear group action on this open disk, and they wanted to study it by linearizing it, by mapping it to something else where the group action would be easy to understand. And that sort of motivated their discovery of, well, of a map like this, which is perhaps very, suggests that P-adic geometry is very far from usual complex geometry. And let me also emphasize, this is not a universal cover of the projective line. That is the domain of this map, this open disk. That's not simply connected. It also has lots of covers. So actually, in this world of P-adic geometry, you should think essentially nothing is going to be simply connected. The open disk is not simply connected. The closed disk is not simply connected. The analog of the Riemann sphere is not simply connected. Those are, well, if anything was going to be, those would be, and they're not. Okay, so you might get discouraged and think that these covering spaces are not such a good thing to study here, but let's not get discouraged and let's go on to genus 1. So again, let's start by thinking about the complex case. So curves of genus 1 over the complex numbers are elliptic curves. And as I told you earlier, every elliptic curve looks like you took the complex numbers modulo the action of a lattice by translation. And you can always normalize so that lattice is generated by 1 and tau, where tau is some point in the upper half plane. And in that case, the covering that you have from C to your elliptic curve can be factored in 2 steps. So you can first mod out by the subgroup generated by the element 1, and then mod out by whatever the image of tau is. So if you take C and mod out by the integers, well, that looks like C star. That looks like the collection of non-zero complex numbers. More precisely, if you look at the function z goes to e to the 2 pi I z, that's a map from C to C star, which is a covering map, and the kernel of that map is exactly the integers. And now if you want to get the elliptic curve E, you should take C star and further mod out by a cyclic subgroup. Now it's the cyclic subgroup generated by the element Q, which is e to the 2 pi I tau. And since tau is in the upper half plane, this complex number Q has absolute value, which is strictly between 0 and 1. And so this is one way that you can analyze elliptic curves over the complex numbers. They can all be presented like this. And now we can ask what happens in the world of P-adic geometry. So let's start with the good news. So the good news is if you have an element Q whose absolute value is strictly between 0 and 1, and now by absolute value, I mean this P-adic absolute value, then you can do the same construction. You can take CP, or CP star, CP minus 0, and mod out by the cyclic subgroup generated by Q. And that quotient is something that makes sense in this world of rigid analytic geometry. And it always gives you something algebraic. It gives you actually an elliptic curve. So I think this was one of Tate's original motivations for developing this theory, was he wanted to study this construction. He wanted to describe elliptic curves as the quotient of CP star by a cyclic group. So the good news is you can do this construction, but the bad news is you don't get all elliptic curves this way. In fact, Tate proved that an elliptic curve can be obtained in this way if and only if it has bad reduction. So that means that if you write down, if you try to describe your elliptic curve as the set of solutions to some polynomial equations, it always has the feature that when you reduce the equations mod p, you get something with singularities. So this is, let's say, not the generic behavior. So for example, if you took an elliptic curve, which is defined over the rational numbers, then you can think of it as an elliptic curve over CP for any prime number P that you like. And this bad reduction behavior, it's only going to happen for finitely many primes P. So for example, the elliptic curve that I mentioned earlier, the one that's given by this equation, if I did my arithmetic right, it has bad reduction when p is 7, 17, and 41,000 something. And so at those 3 primes, this you could use rigid analytic geometry and study this kind of uniformization and get some information about what the torsion looked like. And at any other prime, well, this theorem would not apply. Okay, so that was about one step in the complex analytic uniformization of elliptic curves. That is, writing an elliptic curve as a quotient of C star. If you really wanted the universal cover of an elliptic curve, you should then take the universal cover of C star, which in complex geometry, you can understand using the exponential map. So C star, the universal cover is C, and you can realize that explicitly via the exponential map. Z goes to e to the z, which is given by this power series expansion, which converges everywhere. And it converges everywhere because these coefficients 1 over n factorial go to 0 very quickly. That's the usual Archimedean story. And this is not how it works in the P-adic numbers. Because remember that to be small in the P-adic topology means you have lots of powers of p in the numerator. These coefficients 1 over n factorial have lots of powers of p in the denominator, which means that actually these coefficients in the P-adic sense, they're growing very quickly. They actually grow exponentially. So you get something that actually get a power series, which in the P-adic sense, it converges, has a finite radius of convergence. It converges somewhere, but it doesn't converge everywhere. So this actually gives you a partially defined map from CP to CP star. It's defined on a certain open ball. But this map is not surjective. And in particular, the image of this map doesn't contain any of the elements Q from the previous slide. On the previous slide, I said, you want to take C star modulo elements which have absolute value between 0 and 1, and no such element arises as the exponential of something. So in particular, the idea that you could uniformize an elliptic curve by writing it as a quotient of the complex plane, or uniformize C star as a quotient of the complex plane, those don't carry over to P-adic geometry in an obvious way. So what if you really wanted to understand, what if you really wanted to fix that somehow? So the problem is we can't write down an analog of the usual exponential map, which gives you the universal cover of C star. But instead of looking at the universal cover, let's look at some finite covers. So the Riemann surface C star has other connected covering spaces. For example, well, the connected covering spaces are exactly given by realizing C star as a cover of itself via the map Z goes to Z to the n, where n is some positive integer. And these maps, there's no problem writing down the P-adic analog of this. It's just given by exactly the same formula. It's not a power series anymore. It's just a polynomial, and it converges everywhere. And so these don't give you the universal cover of C star, but they give you what you can think of as approximations to the universal cover of C star, where the approximation gets better as n gets larger, or more precisely, it gets better as n becomes more and more divisible. So what happens if you try to exploit this idea by taking these approximations and taking some kind of an inverse limit? So let's first try thinking about that over the complex numbers. So let's take the map from C star to itself given by raising the coordinate to the pth power. So that's a p-fold covering map, and just take the inverse system where everything is C star and all the transition maps are given by Z goes to Z to the p. And now what happens if you take the inverse limit? Well, That's a perfectly sensible topological space. But it's not a complex manifold anymore. In fact, it's not even a manifold. It's an example of a topological space which is connected but not path connected. So it can't be a manifold. So it's maybe something you might think of it as pathological. If you want to understand it more concretely, X is something that you can get as a quotient. For X has a group structure, and as a group, it's a quotient of C plus the p-adic integers by the cyclic subgroup generated by 2 pi I comma 1. So this is somehow, so this C is appearing as the actual universal cover of C star, and this construction is producing something which is kind of a p-adic variant of that. It would be the universal cover if you were modding out by, if you took C plus Z modulo this cyclic subgroup, you would just get Z, but instead you took C plus ZP. So it's some approximation to the universal cover, but the virtue of this is that it's something which makes sense, or is going to make sense in the rigid analytic case. So in rigid geometry, you can consider the same inverse system, but now think of everything as a rigid analytic variety. And it's just like over the complex numbers, over the complex numbers, there was an inverse limit that you could think about, but it wasn't a manifold. So here, this doesn't have an inverse limit in the framework of rigid analytic varieties, which are like the p-adic analog of manifolds. But it does have an inverse limit in a larger framework, in a more general category of objects that was introduced by Huber called the world of adic spaces. And in fact, this inverse limit is an example of a very special kind of adic space called a perfectoid space, which was introduced by Peter Schulze about 10 years ago. So let me just give you a picture here. The rigid analytic varieties, the objects we've been talking about that are like the p-adic analog of complex manifolds, they sit inside this larger world of adic spaces, and these perfectoid spaces also sit inside this larger world. And these two classes of adic spaces have essentially no intersection. Something like a point is both a rigid analytic variety and a perfectoid space, but that's about it. But nonetheless, perfectoid spaces, it turns out, could be very useful tools for investigating rigid analytic varieties and things that come from algebraic geometry by the mechanism that I described earlier, right? Earlier I said, maybe you're ultimately interested in compact Riemann surfaces, and then, well, the open unit disk, why should you allow that? Well, it's because even though the open unit disk doesn't come from algebraic geometry, it has lots of maps to things that do come from algebraic geometry. And in fact, any Riemann surface can be covered by open disks. And Schulze proved an analog in this setting that any rigid analytic variety, in some sense, locally looks like a perfectoid space. You can cover it by things that are perfectoid spaces. And this is something that's proven to be tremendously powerful because these perfectoid spaces they're very local in some sense. A lot of things that you might want to do simplify when you're trying to do them on a perfectoid space. So I just want to close by giving one sort of example of this idea, which I found very interesting. So let's go again back to complex analysis and talk about the generic case of uniformization. We've talked about things where the universal cover is the Riemann sphere and where the universal cover is C, but most Riemann surfaces are hyperbolic, meaning that the universal cover is the complex upper half plane. And in this case, you can realize X as a quotient of the complex upper half plane by some discrete subgroup of its automorphism group, which is something we completely understand. That's the group PSL2R. And let's just consider some examples. So an example is you could take the subgroup of PSL2R, which is the image of this group typically denoted by gamma of n, That means it's matrices in SL2Z that are congruent to the identity mod n. So that's as long as n is not too small, that maps to a discrete subgroup of PSL2R that acts without fixed points on the upper half plane. And you can form the quotient and you get what's called an open modular curve, denoted by y of n. And this is a construction that you can do in the world of complex manifolds, but these modular curves come from algebraic geometry. In fact, it's even better than that. They're not just they don't just come from algebraic varieties over the complex numbers, they come from algebraic varieties that are defined over Q bar, in fact, even over Q adjoin an nth root of unity. And therefore, you can consider not only their incarnation in the world of complex geometry, but also their incarnations in the world of rigid analytic geometry. These have associated rigid analytic varieties by yn analytic. And as n varies, you can organize these into an inverse system. So this is kind of like what we were doing earlier with C star, but now, well, it's more interesting because the sort of relevant group is something non-abelian. So this gives you a tower in the world of rigid analytic varieties. And just as before, you can't take the inverse limit of this tower in the world of rigid analytic varieties, but you can take this inverse limit in the world of adic spaces. And Schulze proved that if you do this, then you get an example of a perfectoid space. And so you should think of this object as some kind of P-adic counterpart to the complex upper half plane. And this theory of perfectoid spaces is giving you a language to express, well, it's giving you a world in which this object lives. All right, I think that I will stop there. Thank you very much.
In a complex geometry, the open unit, the open disk and the poly disk are not biholomorphic. How is that in the P-adic?
Well, I don't know what the open disk means, if not the polydisk, because of this ultra metric thing.
Is it possible to describe Gross-Hopkins Galag group? You mentioned certain cover constructed by Gross-Hopkins of P1. Is it possible to describe the Galag group of this cover?
It's not Galois.
No,
It's
okay,
possible
normalization.
Right, so the picture is that there's something that the GL2QP is acting continuously on, and the domain of the Gross-Hopkins period map is what you get when you mod out by SL2QP, and the target is what you get by when you mod out by the entire group. So yeah.
Well, would you like to give us an example of an open problem that people are working on here? Or was recently solved? So.
Not sure that I would. Maybe I should begin with a disclaimer. There's lots of experts here, and I'm not one of them. So, you know, I'm covering for Bhargav, who really should have been the one giving this lecture. But I invite experts in the audience to suggest an answer to Karen's question.
Well, like, what is the structure on the cohomologies? These things, like we saw some talks in the postdoc talks.
Sally's talking about what is the structure of the P-adic cohomology of like an open disk, and that's sort of answer when you use these perfectoid covers to sort of try and answer these questions. Some other questions people are interested in are like, what is the cohomology of this limit of, and these finite little things are classical modular curves, like cohomology is well studied in the language program. When you take this limit, you get something else that showed up previously in the P-adic language program, but this extra structure that's the cohomology of this thing called a perfectoid space gives you new ways you can compute that thing. There's a lot of really exciting work like Lurie at Princeton and one S one comparability.
That's an answer. In other words, you're computing cohomology.
Yes, you can
That
really
may
compute
not
a
would-
lot of things with this actually.
But you use a lot of words that look a little bit like differential topology, but as far as I could make out from the postdoc talks, have nothing to do with.
Maybe one answer to your question, which is closely related to this. So in ordinary complex geometry, let's say you wanted to understand the cohomology of a complex manifold. So that has a definition that you can apply to any topological space, but for a manifold, you can compute it using a de Rham complex.
Yeah.
And so in the case of a complex manifold, that's giving you a relationship between cohomology in the constant coefficient sense and cohomology in the holomorphic coefficient sense. And so one thing that this theory of perfectoid spaces is really good for is understanding things like that in the P-adic setting, things that relate étale cohomology, which is like constant coefficient cohomology, and coherent cohomology, which is related to holomorphic functions, things like that.
Thank you.
So you started with rational points on elliptic curves.
Yeah.
Does all this theory lead back to something about rational points, for example?
Yeah, I just chose that equation at random, and I have nothing to say about it other than the points of bad reduction.
But oui, for that you need multiplicative bad reduction.
What's that?
For that you need multiplicative bad reduction.
Wait, sorry, is it,
You could
if we're over CP, is that?
no, see, but for you have this Q, and so I don't know how you compute the.
Yeah, so my claim that these are the primes where you could use this to get information, well, depending on exactly what you mean by get information, you should worry about that.
At some point, you give this example of CP, and this covers given by Z to the ZP. So
Yeah.
you have a reason to take the same P.
But,
And does it?
no, you could do that for other, you could do that for L rather than P. But my statement that that's a perfectoid space would no longer be true. I mean, that would be some inverse limit that you could take that would not live in this world of perfectoid spaces. So I chose P to segue into mentioning perfectoid spaces.
Do the limit at P first and then at L, it's still perfectoid space.
Sorry?
If you do the limit at P first and then also the limit at L.
Yeah.
that is perfectoid space.
But do at least P. So sorry, I didn't say what a perfectoid space was, but maybe I should just say it's something that you get by a process like that. Like examples of perfectoid spaces are like things that you get by adding a lot of Pth roots of something.
Okay, if there are no other questions, let's thank Jacob.